Hey everyone, my name is Jessica, and today we're going to solve a limit problem using L'Hopital's rule, and also some log properties to help us out a little bit. But let's recap on what L'Hopital's rule actually says. If we're trying to take the limit as x approaches c, which can be some finite number, or positive or negative infinity, and f of x over g of x creates some indeterminate form, which is either 0 over 0 or infinity over infinity, has to be one of those two for L'Hopital's rule to apply, then we can just take the derivative of the numerator and the derivative of the denominator and take the limit again, which is very useful in the problem that we're about to solve. So let's take a look. Right here we have the limit as x approaches infinity of the square root of x minus 1 over 1 to the power of 1 over the square root of x. There we go. So right away we see that we have those two functions, the f of x and g of x function that we were just talking about with the square root of x right here and 1 over the square root of x right here. But they're not really in that f of x over g of x form that we just saw, so it might lead to some problems when we're taking the limit. So let's take a look. Let's say that y of x equals the square root of x minus 1 to the power of 1 over x, like that. And if we took the limit of it just the way it is, the limit as x approaches infinity of y of x, what will we get? We would put infinity into the square root of x right here, and we would get infinity. And we'd put an infinity up here also, and we'd get 1 over infinity, which is 0. So we would get infinity to the power of 0, which definitely is an indeterminate form, but it is not 0 over 0 or infinity over infinity, which means that we cannot use L'Hopital's rule yet. But luckily, we can do a little bit of rearranging up here and hopefully get it into the right form. So let's take the log of both sides of our little equation. And by log properties, if we take the ln of this right here, we can bring this exponent, 1 over the square root of x, down in front. So we can say that this is ln of the square root of x minus 1 over the square root of x. Okay, so if we took the limit now, the limit of ln of y of x, what will we get? We would get, if we put, as x approaches infinity, and we put an infinity into this ln, we would get infinity. And then if we put infinity down here, the square root of infinity, still infinity, and we get infinity over infinity, which is definitely one of the indeterminate forms that we can use. So that's good news. We can use L'Hopital's rule now. Let's take the limit as x approaches infinity of ln of y of x, and see what we get. I'm going to leave a little bit of space here. So if we take the derivative of the numerator, we get 1 over all the stuff on the inside, which is the square root of x minus 1, multiplied by the derivative of all this inside stuff, which is going to be 1/2 x to the negative 1/2, and we'll just leave it like that for right now. And the derivative of the denominator, which is also 1/2 x to the power of negative 1/2. And would you look how convenient that is? These cancel out. So what are we left with? The limit as x approaches infinity of ln of y of x equals 1 over the square root of x minus 1. And if we put infinity into this denominator down here, we get 1 over infinity, sort of, which equals 0. Which means that L'Hopital's rule did work. But this 0 is the limit of ln of y of x, and we are just looking for y of x, which means that we have to manipulate it around, manipulate it back. Since what we did up here to take this limit was take the ln of everything, it seems very fitting that we raise our answer by e to get what the limit of y of x is. Let me move this down a little bit. Okay, so if we're this time just taking the limit as x approaches infinity of y of x, we should get e to the power of 0, which equals 1. And 1 is our answer. I hope that made sense and you understand this a little bit better. Good luck in the future, and thanks for watching.